Hi, my name is Jesus Sanz, and this is my lab Motion of a Falling Object. Introduction. For an object, if there is a change in velocity over a change in time, which is equal to the net force divided by mass, then there has to be a force present on the object. Now, the purpose of this experiment is to observe Newton's second law of motion for an object moving at a changing velocity as a result of the weight and drag forces. W equals mass times g times the negative j hat, and Fd drag force equals the proportionality constant b times j hat times the velocity magnitude squared. Now, in my experiment, I dropped a ping pong ball and tracked its fall using Tracker. The goal of this experiment is to find the constant for which the model and tracker data are most correlated. And here are the important formulas that you're going to need. That's a velocity formula, change in position over change in time, and the final position formula, which is the initial position plus the average velocity times the change in time. Now, here are the steps for the experiment. They're pretty simple, but you're going to record a video of a falling object in motion, insert the video into Tracker software, use the data in Tracker to create a model on GlowScript, and then insert the data into Sheets software to get graphs. And you're going to want to add drag to the model as well. And here's the Tracker video itself. So as you can see right there, I dropped the ball, and the point mass was calculated in each frame. And then here in the bottom right here, we can see the data values right there. So here we have the GlowScript diagrams, which we're gonna get from the GlowScript code, and I'll show you guys that code shortly. But you're gonna get this quadratic graph right here, and here's an actual visual diagram to further understand. Now, the experiment versus model with no drag, and that's important here, no drag. So this model had very different results from my experiment. The difference between the final position of the model of the experiment are significant. So we know the model is missing a crucial piece. While yes, both lines are accelerating downward, negative slopes, we know based on the displacement by time being in the shape of quadratic functions for both lines that one is accelerating at a much slower rate than the other. This one compared to this one. All right, so you're gonna notice something weird about this one, and this is because I made a mistake. So the model is fine, as you can see. It's exactly the same as it is in the last graph. Same slope, everything, and the model with drag. Apparently, this is what it's supposed to look like, and I believe this to be correct. But for some reason, the experiment, when I input it, like put the values in, it has a positive slope now. It's a completely different graph. So that's a complete error on my part. You're also going to notice these two lines right here, this red line, which means absolutely nothing, and this blue line right here, which I'm not sure why that occurred, but if you just imagine that these two lines aren't there, this is what it would look like. Other than this experiment line is really, it looks like this. So if you're able to visualize that, then that means that the model with drag and the experiment are very much the same. And that means that the second model works much better than the first model. As we can see that there's a lot less space between the yellow line and the blue line. And while it's not a perfect match, it definitely means the object's motion is much more effective on this. Now, as far as the what if questions go, if one of the models is to be terminal velocity, then it has to be a constant. It has to be pretty constant velocity. And that's going to be the model with drag, the yellow line, right? Because this line is much more linear than the red line, and that indicates a more constant velocity. As we know from Newton's second law, a constant velocity means a net force of 0. And as for the second what if question, what if the object was initially thrown downwards? Well, it's going to have a higher terminal velocity due to that initial throw in the negative y direction. And here's the GlowScript code, so we can check it out. And probably the most important thing to note about this GlowScript code is this right here. These three lines of code. So the W, and the FD, the weight force, and the drag force right here. So in order to get the net force with weight and drag force, you have to add this drag force right here, which, as we stated, these are the two formulas. We're using them right here, putting it into play, so that we're able to calculate the net force with the drag force, and then we subtract that FD, that drag force, with without the drag force. So that's pretty cool, and that's probably the most important thing to note. As far as that goes, that's my lab, that's my project. Thanks for watching.